Where does our solar system actually end? Chances are you've probably wondered about that at least once in your life. So where exactly is that invisible boundary, the line that separates the world we live in, our solar system, from the endless mysterious space between the stars? And who decides where that boundary should be drawn in the first place? On this side, we've got the familiar world protected by the sun, our world. But on the other side lies a strange, freezing alien realm we've never seen. So how in the world do you mark the border between something we know and something so completely unknown? Or maybe, just maybe, that boundary doesn't even really exist, and it's just something we've imagined in our minds to help us make sense of it all. Hey everyone, welcome! It turns out that boundary actually does exist. And not only is it real, but it's more than just a line. It's been described as a kind of wall. But not just any wall. This one is made of fire. A wall so intense, it's 10 times hotter than the surface of the sun. And yet, against all odds, the brave little spacecraft Voyager 1 and Voyager 2 pushed through that blazing wall and kept going. Sounds impossible, doesn't it? Then hit that subscribe button because we're about to dive in and explore this mystery together. Alright, let's get started. Messenger to the Stars, Voyager 1. The first to detect this astonishing phenomenon, the blazing wall of fire, was none other than the space probe Voyager 1. It became the very first human-made object in history to break free from the solar system and head into the great unknown. Voyager 1 was launched way back in 1977. That was an era when computers still ran on punch cards, and the massive Titan III rockets, which now feel like relics from the Cold War, were being routinely rolled out onto launch pads. At the time, the main goal of the mission was to study Jupiter and Saturn up close. But from the very beginning, both the design of the spacecraft and the trajectory it would follow were built with something far more ambitious in mind. It was meant to go beyond the edge of the solar system, into the vast emptiness of interstellar space. That's why Voyager 1 was equipped with the famous Golden Record, a message from Earth intended for any extraterrestrial life that might find it. The record symbolized humanity's first voice sent into the deep, dark reaches of space. It carried the sounds of our planet, music, images, and even a map that explained where in the universe to find Earth. All we can do now is hope that hundreds or even thousands of years from now, if some alien goblin stumbles across that record in deep space, it won't follow the coordinates and launch a Herbert Wells-style war against us. Voyager 1 is powered by the decay heat from plutonium in its nuclear battery, and even now, nearly 50 years later, it's still flying through space, taking over 20 hours to receive commands sent from Earth. Then, in 2012, the probe made a discovery that completely overturned our understanding of where the solar system ends. Its instruments recorded a sudden and dramatic spike in temperature. The readings shot all the way up to 90,000 degrees Fahrenheit. That's nearly 10 times hotter than the surface of the sun. At the far edge of the solar system, in a place we thought was ruled by cold and vacuum, the spacecraft had run into a literal wall of fire. So what exactly is this strange phenomenon? Why is there something that looks like the sun's corona burning in the middle of the vacuum of space? To figure that out, we need to take a closer look at the true nature of the solar wind. Wall of fire. The sun isn't just a star that shines by emitting visible light or photons. It's constantly blasting out a steady stream of charged particles, including electrons, protons, and ions, into the vastness of space. This invisible stream of particles is what we call the solar wind. The solar wind shoots outward in all directions at a staggering speed of 500,000 miles per hour, creating an enormous bubble around the sun known as the heliosphere. Imagine a soap bubble floating in a stream of water. That's the kind of structure we're talking about. Except this bubble isn't made of soap, of course, it's made of magnetic fields and energetic particles. And the surrounding water in this analogy? That would be the thin, sparse gas and dust that make up the interstellar medium. The outer boundary of this vast bubble is called the heliopause. It's the point where the solar wind starts to weaken and can no longer hold its ground. And right at that boundary, something dramatic happens. A collision takes place. The solar wind, which moves at speeds that are considered supersonic in the context of space plasma, suddenly slams on the brakes. It's similar to what happens in front of an aircraft's nose, where air gets compressed and forms a shockwave. That shockwave squeezes the particles together and heats them to absolutely extreme temperatures. And that's exactly what Voyager 1 detected as it crossed into this fiery region. But then the question is, how did the probe survive without getting burned up? The truth is, in outer space, high temperatures don't feel hot the way we experience heat on Earth. Temperature out there refers to how fast the particles are moving, but the particles themselves are so few and far between, they're barely there at all. It's kind of like being hit by a single drop of boiling water. You might feel something for a moment, but it's not going to cook you. Sure, you might notice a tiny sting, but it's nowhere near enough to boil anything alive. To be clear, even the sun's surface temperature, around 9,900 degrees Fahrenheit, doesn't refer to a dense material like metal, but to a super thin cloud of plasma. The magnetic mystery. But the wall of fire, as incredible as it was, turned out to be just one small piece of the puzzle. When Voyager 1 broke through that wall, its instruments detected something even more surprising and completely unexpected. Scientists had been waiting for this moment with eager anticipation. At last, the spacecraft was escaping the heliosphere. And with that, the magnetic field around it should have changed dramatically. The sun's magnetic field was supposed to give way to the galactic magnetic field beyond. Everything pointed to that outcome. It all made perfect sense. That's exactly what everyone had been expecting, but it didn't happen. The magnetic field outside the heliopause turned out to be almost identical to the one inside. It was as if Voyager hadn't escaped the sun's reach at all, but was still drifting through something even larger and more encompassing. At first, scientists assumed it was just a coincidence, maybe some local irregularity or anomaly in the data. But then, 6 years later, Voyager 2 also crossed the heliopause. It took a completely different route, traveling far to the south of Voyager 1's path. And yet, Voyager 2 recorded exactly the same result. Two probes, taking two entirely separate trajectories, came back with the exact same findings. What they revealed was that the magnetic field was perfectly ordered. In fact, it was almost completely aligned. This challenged everything we thought we knew about where the sun's influence ends and where the galaxy begins. Could it be that the galactic magnetic field is far more structured and organized than we ever imagined? Or maybe, just maybe, the very structure of the heliosphere itself is much more complex than a simple floating bubble in space. All of this is based on direct physical measurements. Not guesses. Not computer simulations. This is real data, transmitted across billions of miles by a spacecraft launched nearly half a century ago. And right there, at the farthest edge of the solar system, a true scientific revolution quietly began. This discovery marked a turning point. We now know that the boundary of the solar system isn't a clean, sharp line, but a wild, turbulent, and deeply complex zone where our world and the interstellar realm clash and intertwine in powerful, dynamic ways. The shield of our universe. But why does any of this really matter in the first place? It's because the heliosphere acts as our cosmic shield. This enormous bubble created by the sun is what protects Earth and every form of life on it from the deadly rays of the galaxy. High-energy particles so powerful they can tear through metal and shatter DNA. Every so often, something monstrous comes barreling toward our solar system, something like a giant invisible dinosaur. And compared to that, the particles smashing together inside the Large Hadron Collider are nothing more than blind little kittens playing in the dark. The most energy we can generate in the collider when two protons crash into each other is about 14 tera-electron-volts. That's a 1 followed by 13 zeros. But in space, the highest energy cosmic rays ever recorded reached levels as high as 10 to the 20th power. That's 10 million times more energy. Just try to imagine what would happen if we didn't have this shield in place. Those dinosaur-sized particles would come stampeding toward Earth in endless swarms, crashing into our atmosphere like a cosmic stampede. Understanding exactly where this shield begins, how it's built, and what takes place at its outer edge isn't just a matter of scientific curiosity, it's a critical issue for the safety of future space missions. A new scout, IMAP. And that's exactly why NASA is now preparing to launch its next cosmic scout. This new space probe is called IMAP, the Interstellar Mapping and Acceleration Probe. It's designed to follow in the footsteps of Voyager, but it comes with an entirely new set of capabilities and a different approach. IMAP isn't heading into deep space. Instead, it will remain in place at a special location just 930,000 miles from Earth, where the gravitational pull of the Sun and Earth perfectly balance, a spot known as a Lagrange point. From there, the probe will be able to continuously monitor the solar wind without being disrupted by Earth's magnetic field. IMAP's mission is to create a full 3D map of the edge of the heliosphere. It will track exactly where this bubble-like shield around us begins, how it changes over time, and where, specifically, it collides with the cold and merciless vacuum of interstellar space. IMAP will focus on detecting what are known as energetic neutral atoms, streams of particles that reveal what's happening at the boundary. These are particles born right at the front line, where the solar wind slams into the interstellar medium. Just like bits of driftwood washed up on a shoreline can tell us something about the tide, these particles carry traces of the powerful processes unfolding out there. In essence, IMAP will act like a kind of X-ray for the universe. It will reveal the true shape, structure, and inner workings of the heliosphere, how it breathes, how it moves, how it holds. And it will tell us where the Sun's influence fades away and what lies beyond it. This knowledge isn't just important for scientists. It matters for anyone who may one day journey farther than the Moon. Because out in deep space, there's no atmosphere, no magnetic field, nothing to shield us. That means we absolutely need to understand where our home ends. IMAP isn't just another space mission. It's our first real attempt to look back at the solar system from the outside in. It's an effort to see the solar system as a tiny island floating in the vast ocean of the galaxy, and to finally discover where that ocean truly begins. Just one light day. Even now, Voyager 1 and Voyager 2 are still flying through that vast galactic ocean. One is heading north, the other south. Both have long since passed Pluto and are now venturing far beyond every region humanity has ever mapped, deep into a silent, unexplored darkness where the Sun has shrunk to nothing more than a tiny dot in the sky. More and more often, the probes fail to respond. Their signals are fading, and their power is quickly running out. And yet, they keep going. From within the darkness no human has ever set foot in, they continue to send back precious fragments of knowledge. Voyager 1, traveling at a speed of 11 miles per second, that's about 334 million miles per year, is still moving farther and farther away from Earth. And this November, it will reach a distance of one light day from Earth, roughly 16.1 billion miles away. It's a humbling reminder of just how small and fragile we truly are. It's taken nearly 50 years to travel the distance light covers in a single day. The nearest star to us, Proxima Centauri, is 4.24 light-years away. At Voyager's current speed, it would take around 73,000 years to get there. But no, Voyager will never make it to that star. Neither Voyager 1 nor Voyager 2 is heading in that direction. Voyager 1 is currently traveling toward the constellation Camelopardalis. The closest star along its path is AC plus 793888, which lies 17.6 light-years from Earth. Voyager 2, on the other hand, is moving toward the direction of the constellation Telescopium. The closest star along its course is Ross 248, and that's still 10.3 light-years away. But that's okay. Even so, humanity has already accomplished something extraordinary. And we believe that going forward, we still have billions of years ahead of us. If you found this video fascinating, don't forget to give it a like and share it on social media. Thank you so much for watching. Until next time, take care and goodbye.